we are going to start our next chapter with related rates. And these are actually some of the most real-life applicable places where you'll find calculus. So it'll be really exciting, hopefully. And you guys will be able to see how we can put everything together that we've learned so far. All right, so with related rate problems, you're probably looking at this going, oh my goodness, 8 steps. Really, the big ones, the big ideas here are that we need to write a non-specific equation. We need to simplify that equation, and then we differentiate both sides. But when we differentiate both sides, we are not differentiating with respect to x or y this time. So this is like implicit differentiation, but we are differentiating with respect to t. So that means we're going to do implicit differentiation, and we have to tack on, in an essence or in a sense, an x prime and a y prime, not just a y prime, because these are all done with respect to t. And I'll show you how that works. We are actually going to use our other notation instead of doing y prime and x prime. We are going to use this notation that you see down here in example 1, dx dt and dy dt. So this really just means x prime, and this really just means y prime, but with respect to t. So that's going to be really important for this process. All right, so let's go ahead and take a look at this first example here. All right, this says, first read the problem carefully. Hopefully, this problem isn't too in-depth. Looks like a circle centered at the origin with a radius of 5. Draw and label a diagram if possible. Well, we could sure draw that circle, but in all honesty, we don't need to because we have everything that we need. I've actually also already given you number 3 because it says list what you know and represent it using derivative notation with respect to time. Well, that's exactly what dx dt is. It says list what you need to find. Well, I also gave you that. I'm asking you to find dy dt. All right, so the next thing, and we also already have the non-specific equation, so I'm starting you off fairly easy, and it's already been simplified. So it looks like we are ready to do number 7. We're going to go ahead and differentiate both sides. So if we differentiate x squared, we'd get 2x. And now, as I said, we technically need to tack on like the x prime to this because this is with respect to t. But instead of x prime, we're going to replace, or we're going to tack on dx dt. All right, and then I have plus 2y, and again, it should be y prime, but we're going to go ahead and tack on dy dt. We're going to use this notation instead. And then that equals, well, the derivative of 25 is just 0. All right, now it says for number 8, now that we've done our differentiation, substitute known values and simplify. All right, well, we were given dx dt. We were told it was 6. We were also given x. And actually, we could find y, because if x is 3, then we know y is 4, because this would be a 3, 4, 5 triangle. 3 squared plus 4 squared equals 5 squared. All right, so with that in mind, we're going to say 2 times our x, which is 3, times our dx dt, which is 6, plus 2 times our y, which we found to be 4, times, and what we don't know is dy dt. And that's what we're trying to find, so that's what we want to get by itself. All right, if we go ahead and multiply here, all right, so we end up with 6 times 6, which is 36. So we have 36 here, plus 8 dy over dt. Then I'm going to go ahead and subtract 36 from both sides. And I'm going to move this up so we have some more room. Subtract 36 from both sides, so we get 8 dy dt equals negative 36. And when I divide both sides by 8, I get dy over dt, and that's what we wanted to solve for. So we've got it by itself. Well, negative 36 divided by 8 is negative 4.5. So our final answer is that the y is changing with respect to time when x equals 3 and y equals 4 at a rate of negative 4.5 units per whatever the time would be. All right, let's go see an actual example that has a little more meaning, a little more real-world information to it. So our next example deals with a square, and the square is increasing its side lengths. So if you look at this, so again, we're supposed to read these questions carefully, so maybe go ahead and pause the tape for a second and read through it. And now when you come back, it says each side of the square is increasing at a rate of 6 centimeters per second. So the square is growing. The sides are growing. All right, so if we think about our problem here, we're supposed to draw and label a diagram if possible. Well, this one is possible to draw and label a diagram. I'm going to go ahead and say that this is x and this is x because we know that. It says that the sides of the square is increasing at a rate of 6 centimeters per second. Okay, a rate is automatically a derivative. We know that. So we're saying that x is increasing. So I'm going to say that the rate as x increases with respect to time is 6. So I found dx dt. This says at what rate is the area of the square increasing? When the area, so in other words, it just asks us to find dA dt. At what rate is the area increasing? That's what we're supposed to find. And then it says when the area is 16 square centimeters. Okay, so if the area is 16 square centimeters, that would mean that x has to be, hopefully you came up with 4. All right, now we are being asked to find the rate at which the area is increasing. And so it would make sense for us to go ahead and write the area function because that's our next step. It says, okay, draw and label, list what you know, we've done that. List what you need to find, we've done that. Write a non-specific equation. So we're going to write a non-specific equation. What I mean by that is that we don't want any numbers in it. We just want the variables. So it would work for any case. I don't know if you guys can hear that, but that's beautiful. There is a red robin sitting right outside my window. Oh, how cool. So he's chirping like no other. Oh, cool. Okay, anyway. All right, so we're going to go ahead and find the derivative now because we've got our non-specific equation, so we're going to differentiate this. So we have dA dt because the derivative of a would just be 1, but we're not differentiating with respect to a, we're differentiating with respect to t, so we have to tack that dA dt on. And then we'd have 2x dx dt. Again, we differentiated in x, we have to tack on the dx dt. So we're ready now that we've done our simplification or our differentiation and we have simplified, we are ready to plug in what we know. We're trying to find dA dt, it's already by itself, so that'll be great. We're trying to find this when x equals 4 and dx dt equals 6. So now if we go ahead and just multiply that across, we get 48. So we know that the area when the x values, when the sides are increasing at a rate of 6, so when x equals 4 and the area is 16 and it's still increasing, that area is increasing at 48 centimeters squared per second. That's the rate that the area is growing. So hopefully that made a little more sense. Now we're going to go on to even yet another. All right, our next example, it would be as if we have a spherical balloon, so if you can imagine just blowing up a balloon, and the volume is increasing at a rate of 100 centimeters cubed per second. Another thing you could think of is if you were doing like a water balloon fight and you were filling up the balloons, and water would be pumping into the balloon at a constant rate, and the question is how fast is the radius of the balloon increasing? So again, hopefully just read through this, take a look at it, and we want to write a generic equation. We want to find our different related rates. So let's go ahead and first do that. Well, we can draw and label a diagram. So we have the sphere, we have the radius, and the next problem you'll see why it's so crucial to draw the diagram. This one maybe not as much, but then we're supposed to list what we need to represent. We're supposed to figure out how fast the radius of the balloon is increasing. So we are trying to find dr dt. We want to know how is the radius increasing as the time is passing and the water is being pumped in or the air or whatever it would be. Well, air in this case, but I like to think also of water. Okay, so dr dt is what we're trying to find. That's what we don't know. We do know, however, that the volume, so I'm going to say dv dt, and I'm going to represent volume that is v. We know that that rate is 1,000 centimeters cubed per second. And you guys, a key here on all of these is to recognize that every time you have a rate, it goes with a derivative. So this is centimeters cubed per second. Cubed would be volume per second. So it makes sense that it's the volume with respect to time and how it's changing. So dv dt. Then it says, well, we need to write our generic equation then. So we have what we know, we have what we need to find. We need to write a non-specific or a generic equation. And I don't know if you guys remember the volume for a sphere formula, but volume for a sphere is 4/3 pi r cubed. And now that's also in the front of your textbook. And if you would need to use that on an exam, I would give it to you. I don't expect you to necessarily have that memorized. Okay, A couple other things, though, I guess that we didn't do was we didn't say we had the diameter. We know the diameter is 50 centimeters. And so from that, we can determine that the radius is 25 centimeters. Okay, we have our generic equation. We have everything figured out. We know we're trying to find dr dt, so we're ready to go ahead and differentiate this with respect to time. So we would have dv dt because the derivative of v would be 1, but it's not a t, so we have to tack on v prime, which would be dv dt. And now, if we differentiate the next one, we can think of this whole thing as like a coefficient to r. So we would have the 4/3 pi, and then if we differentiate the r, it'd be times 3r squared. And with this, the 3's would reduce, getting us just 4 pi r squared. But now we also have to be concerned because we did differentiate an r, so we would need the dr dt tacked on here, which means there's a dr dt tacked on here. All right, I'm going to go ahead and slide this up a little bit here, and we have dv then dt equals 4 pi r squared dr dt. And now that we have our derivative and it's all simplified down, we're ready to stick in things that we know. We actually do know dv dt this time, and we know that that was 100. So I'm going to replace dv dt with 100. I know that the radius that we found was going to be 25, so we'll have 25 squared. And what we don't know is dr dt. That's what we need to solve for. So basically at this point, to solve for dr dt, if I'm going to solve for dr dt, I'm going to divide 100 by all of this, the coefficient there to dr dt. So I'm going to divide it by 4, by pi, and by 25 squared. Well, I know that 104 can reduce to 25 over 1, and then that 25 would reduce with one of those there. So we're going to end up with, for our final answer, dr dt is going to be 1 over 25 pi. And if you want to know that approximation, you can go ahead and plug that into a calculator. But I do want to label this. This is the radius. So it would make sense that its label would be centimeters per second. Because with this, if we knew that it was in centimeters from our volume rate, we know that radius is one-dimensional, so it'll be centimeters per second. All right, now we're going to go on to a super fun problem that's going to involve similar triangles. Be a little more complicated, but this gets into more of why we need all the stuff we've done all the way up until this chapter. All right, you might want to go ahead and pause the tape here and just read through the problem carefully. That's our first step. Now that you've read through the problem carefully, let's go ahead and draw our diagram. So I'm going to draw our diagram. We have an inverted cone, which means that the cone part is going down. So here's our inverted cone, and it's a water tank in the ground. And we have that. All right, so the water tank has a radius at the top. Now the radius actually changes the entire time, but the radius at the top we know is 2 meters. And we know the height all the way to the top is also, we know that one, that's 4 meters. But the height and the radius will actually change as the water is moving up, or going up the tank there. So we're pumping the water in. And it tells us that the water is being pumped in to the tank at a rate of 2 meters cubed per minute. Again, automatically I see a rate, I see meters cubed, I know that's volume. But it also makes sense because pumping water in is going to be a volume thing. So I'm going to say dv dt is going to be 2 meters cubed per minute. And then it says find the rate at which the water level is rising. Okay, water level in this case would be height. So I'm supposed to find dh dt. That's what it's asking me to find, but I'm supposed to find that when the height is equal to 3. All right, so I need the generic formula for the volume of a cone. And again, another formula you may not have memorized. That's okay. I'm going to give it to you. And this would be in the front of your textbook if you needed it, but it's 1/3 pi r squared times h. So it's going to be our generic formula. Now, we do have a problem with this formula because we have too many variables in it. And so we're going to have to do something about that. Because we have 2 variables in this equation besides the v, we are going to have to figure out how to replace one of them. And I look at this and I know I'm trying to find dh dt, so I don't want to replace the h. I'm going to want to replace the r so that it's in terms of h's. And if in order to do that, we kind of have to think to ourselves what happens here in this cone as water pumps in. Well, as water pumps in, let's say the water's at this height. So my radius is right there, and then I have this height. If you notice, we have this triangle right here would be similar to this big triangle right there. So with that in mind, I can say that I know the relationship between the radius and the height is technically 1/2. So the radius to the height is 2 to 4. And so, and we could say that that's 1 to 2. And then I know that my generic radius and height are 1 to 2. So if I go ahead and I solve this right here for r, so that I can get r replaced in the original equation, I'm going to have, if I do my cross products, I'm going to have h equals 2r. So if I divide by 2, I'm going to have r equals h over 2. So now that I know that r equals h over 2, to get my most generic equation with only one variable, I'm going to go ahead and replace the r in the volume. So volume will be 1/3 pi. I'm going to replace that r with h over 2 squared times h. And now the great news is I've got everything with dv, or I have everything in terms of volume and height. So when I go use dv dt and dh dt, I'll be good. I didn't know dr dt, so I had to get rid of the r's. I won't know what that is. The other thing is this just eliminated having to do the product rule. So let's take a look at this. Let's go ahead, now that we've got everything done, let's go ahead and do our derivative here. Actually, I want to simplify the volume one more step here. So I'd have 1/3 pi times h squared over 4 times h. So if I simplify that down one more time, I'm going to have 1/12 pi h cubed. All right, so now if I'm ready to go ahead and do the derivative, I would get dv over dt for the left side, and the right side, the 1/12 pi is really just a coefficient, it's just a number, and then I would have 3h squareds for the derivative, dh dt. Again, because I differentiated an h, so I have to tack on h prime, which in this case, using this notation, we would call it dh dt. All right, so let me go ahead and move this up a little bit here. So we have dv dt would equal, the 3 and the 12 will reduce, so that I have pi times h squared over 4 dh dt. And now I'm ready to go ahead and plug in all the things that I know. I knew the volume. I know the volume is 2. I also know that the height is 3, because that's the time we're finding this at. So 3 squared over 4, and then we have dh dt. So now it's just a matter of solving that and getting dh dt by itself. So I would have, it looks like if I go ahead and multiply both sides by 8, or by 4, I'm sorry, I would have 8 equals 9 pi dh dt. Then if I divide both sides by 9 pi, dh dt is going to equal 8 divided by 9 pi. And that would be, let's see, meters per minute, because that's a one-dimensional thing again. Now, that one I did go ahead and plug into my calculator, and I got about 0.28 meters per second. So that would be the rate at which the height would be changing when the height is 3 for this cone. All right, come see me if you have some questions.